Okay, so we're on to the next bit of chapter 7, which is about finding critical values for a given test. Now, what we went through yesterday was basically just looking at, well, how do we sort of set this test up for a given significance level? How can we set the situation up so that we can actually start testing something, and we can crunch some numbers with it? And we're going to start crunching through some numbers today. And what we're going to be looking at today is the critical values. So in other words, what that means is, if I had, let's say we had the example 2 yesterday about that election candidate that has support of 40% of the residents. They asked 20 people. Now the critical value would be, well, what would the number of people be so that we thought that the 40% was unrealistic? Because we did say yesterday that there would be some natural variation. You know, in a sample of 20, you can't just expect to get exactly 40% with every sample you do. So there has to be some, you know, like allowance of a bit fewer or a bit less. But what would be the first value in a sample of 20 where we'd say, actually, you're talking nonsense, it's not 40%, you can't prove that, and statistically we've found that that's wrong. The critical value is the first value at which we can reject the null hypothesis, the first value at which we can say, actually, this has changed. What we thought was true isn't really right anymore. So we're going to have a look, as I commented yesterday, about assuming that we can use the binomial distribution for all these things. So we spoke about in the prior knowledge check questions about what the conditions are for the binomial distribution. And we're just going to have a look at a little example here about a test statistic is modeled with a binomially distributed with 10 trials, probability of success P, and a hypothesis test at the 5% significance level. Now, these significance levels are going to be fairly important to us throughout this chapter. So we're saying the null hypothesis is going to start off as the probability is 0.4. So that's the idea we're going into this with. We think it's got a 0.4 probability of success. The alternative hypothesis, so have a think about whether this would be one-tailed or two-tailed. So we should have come up with a thought in our heads that that's going to be a one-tailed test because we're only looking greater than 0.4. So somebody else is thinking, well, actually, I think the probability of success is a bit more than 0.4. So we think it's going to be this. We assume the null hypothesis is true. So if we assume the null hypothesis is true, we can now change this section here into this. We can say X is going to be binomially distributed with 10 trials with a probability of 0.4. So with these 10 trials, we can see here that now what we're doing, they've built up a little line graph of what is the probability of getting this number of successes within those 10 trials. So 0 successes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can see here how they've got those values. So you can get those straight from your calculator. 0.0001 with a probability x equals 10. And then you can see on and on from here. And the probability that x is greater than or equal to 8, remember, would be the combination of 10, 9, and 8. Now, if we have a look at what this number is, this is 0.0123. Now, that is a 1.23% chance of 8 or more successes. Now, if we compare that to the 5%, it's less than the 5%. Now, this is what we're looking for. If that probability is less than 5%, we can say, well, that is so unlikely to happen with this scenario. It's so unlikely to happen if the probability of success was 0.4, that actually we can say, well, we can reject this null hypothesis and we can go for the alternative hypothesis. Okay, so if this test statistics comes out as 9, 10, or 8 successes, then we can reject the null hypothesis. However, if we have a look at this, the probability that it's equal to 7 is 0.0425. So if we add it on to what we had before, that's going to take us above 5%. Now, because that is above 5%, it's not as unlikely to happen. So therefore, there is some probability that will happen. our level of significance is going to be the 5% here. So anything that's less than 5% probability, we say that is too unlikely to happen in our sample, therefore we can reject it. If it's above 5%, it's not unlikely enough. Actually, that still falls within our acceptable region of still, we can't reject the null hypothesis off that. So what happens then is the 8, 9, 10 becomes my critical region. This becomes the region at which I'm still going to be happy. The region at which I'm going to reject the null hypothesis. Something has changed about the probabilities we're talking about. In the region 0 to 7, that is an acceptable region. We're not going to reject the null hypothesis because actually it's not unlikely enough for us to start rejecting it. If we turn over, the critical value is the first value to fall inside of the critical region. So on that last question, the critical region was 8, 9, or 10. So the critical value is going to be 8, the first value into the critical region where we are going to reject the null hypothesis. 7 is in the acceptance region. We'd accept the null hypothesis. We wouldn't reject it. Now, we can get binomial distribution tables, and if you have a look at the formula book that you would have been provided for the PPEs, you'll actually see that at the back of that formula book, we have all of these distribution tables, and you can find the binomial distribution table. However, you can do all this through your calculator, and I would maybe advise you now to stop you having to sort of switch screens as you're working on your laptop, or if you're on your phone, definitely it's going to be a bit of a pain doing it. So I would say you can still use your calculator, and you can use that list function on the calculator to list a lot of different outcomes to try and find those critical regions. So if we have a look here, we had n was equal to 10, the probability was 0.4, and we can see as we work our way up that we get these values around here. And we're looking for the first value to be less than 5%. Now, here's the thing. When you look across at the number 7, actually, if you subtract that from 1, it does give you less than 5%. But that includes the number 7. So when I subtract that number away from 1, I'm finding the probability that it was 8 or above. Okay, so just be careful there that I'm not just finding the first figure that when I subtract from 1 gives me something less than 5%, because this 7, as we saw previously, is in the acceptance region. 8 is in the critical region, because less than or equal to 7, if I subtract that from 1, means I'm going greater than or equal to 8. Okay, so we just have to be careful there, and hopefully we'll be able to see that in some of the examples that we do. That just explains what I've just gone through. Now, the actual significance level, so we're testing at a 5% significance level, which means that anything less than 5% we can call our critical region. But what we might sometimes be asked for is the actual significance level. Well, the actual significance level, because the probability of greater than or equal to 8 is 0.0123, so it is less than my 5%, but that now becomes my actual significance level of the test. So it's a 1.23% actual significance level. It's very unlikely we'd ever get something that was dead on 5%. Now, threshold probabilities for the test, the level of significance, are most commonly going to be 1%, 5%, 10%. 10% is going to be the one where we've got the more of a chance of getting into the critical region. Okay, so we're going to be we're probably going to be a bit harsher on the null hypothesis because there's more of a chance of something falling within the 10% region. A 1% is actually allowing the null hypothesis quite a bit of wiggle room. Okay, we're allowing quite a lot of values to fall within the acceptance region of the null hypothesis. And then 5% is somewhere in between. 5% very typical, 10% probably the second most. We do get some 1%, but that allows, as I said, quite a lot of wiggle room for the null hypothesis. So we don't use those too often. That we own that. If we get a 1% significance level, it means we really want to be sure that something isn't right about that probability. Okay, if you flick over to YouTube, we'll have a look at the examples for 3 and 4 before we start exercise 7b.